tell you a couple of things that you're going to look for in this lesson. Okay, so I put up here, I told you that what we're doing is we're going to combine some math learning with some computational thinking learning. And computational thinking is a way of approaching a problem that really helps when you do computer science later on. So we are not going to do any actual coding today, but we're going to use these skills, these ways of thinking in this lesson. You don't need to know what these mean yet. Just have them be familiar to you so that you can recognize them when they show up. Okay? And then there's also some mathematical concepts that you'll see today. My guess is these might feel a little bit more familiar because we've talked about them a little bit. If you are already teaching math, you can stay focused on the teaching math and realize that you're probably already talking about a lot of the things that we're talking about when we say computational thinking. So pattern recognition is a pretty obvious one. But even something in terms of writing an algorithm as steps for how to solve something. When we solve, for example, one-step equations in math, we're going through a series of steps to get to that answer. So what I want you to do now is I'm going to give you, it's time for us to start kind of documenting our thinking. So we've done some good talking, now we need to start documenting it. So I'm going to give you each a handout, and I want you to, with your partner, try to just finish what's labeled as part 1. Okay? And so you're going to fill in, you're going to finish filling in sort of a graphic that talks about these doublings that we're seeing, but also then we're going to try to put the data into a table, because sometimes tables are a really good way to organize our data. One of the computational thinking strategies that I actually did use in this lesson, but I didn't make it explicit to the students, is what we call data visualization. So all we did was take this data and put it into a data table, right? But this allows us to see the data all together. Go ahead and try to find a way to describe that pattern too. You can talk with your partner first before you start writing, maybe?
Pattern doubles each time.
What do you mean by the pattern doubles?
Like the seeds, the spins.
Right, so could we use a different word than pattern maybe so that we could be more specific?
Number of seeds doubles time. Taps.
Yeah, do you see how by saying number of seeds instead of pattern, we're a little bit more specific on what exactly is doubling? Okay, good. So what did you do here?
I think you multiplied 2 times 6 instead of...
Because if we look at our pattern, would it make sense for us to go back down to 12?
No, it wouldn't.
It wouldn't. But do you see why you did that?
Yeah.
What did you do?
I did 2 times 6.
You did 2 times 6, which is a really common mistake for us to make with exponents, right? But if we think about the fact that we see a pattern going, we can pretty quickly see that 12 would not make sense. Exponents can be tricky. A really common misconception that students will have is that they take the exponent and multiply it by the base rather than multiplying the base that many times by itself. Really common error. I actually think this lesson kind of helps us to avoid that, or to be able to recognize it. There was one point in the lesson where I had a student, when they were extending the pattern to 6 doublings and 7 doublings, she wrote on her paper 2 to the 6th and then 12 as the number of seeds. But because she had the table that had all of the previous totals of the seeds, she was able to see that 12 at that point wouldn't have made sense because the pattern would have stopped. So this can help us to address that misconception of what you do with an exponent. Well, let's look back at your algorithm. Okay. So your algorithm, you said start with the base 2. Okay. So you have a base 2. Okay. Find the number of doublings and use the number of doublings as the exponent. So I'm not seeing an exponent here. How could we put number of doublings as an exponent?
S to the power of 2.
So
S equals n to the power of 2.
Almost.
It's s to the power of n times... Wait. S equals 2 to the power of n, which is x, basically.
Right. N is a variable, and s is a variable, right? Because this n, that n right there, is this step where you said You need to add your doubling or your number of doublings, right? But here, what you said, use doublings as the exponent, that's your n. So that works. Having the algorithm first made it so much easier to write the equation. If they had just been starting from even just the data table straight to the equation, I think it would have been a lot harder. So even for myself, having thought about how I wanted to intentionally put computational thinking into this lesson, I was able to see, I'm going to do that more often. Let's write in words what we're trying to do with the equation first in step-by-step form, then we'll write the equation. It's going to be a lot faster. So I was excited that I'm going to try to use that even more as well. Does anybody have any parting questions or thoughts or things on your mind that you want to share? Any final thoughts? Was it fun?
Wait, but how is it computer science?
I thought it was on a computer.
Hold that thought.
Same.
Me too.
Right, so I told you we were doing something related to computer science and we never pulled out a computer, did we?
We
But-
didn't even bring anything in here.
But what we did do was we thought about math in a slightly different way, right? We thought about math using a slightly different way of thinking that allowed us to get to this final part. So computer science isn't always about using a computer to write a code. Sometimes we have to be able to approach a problem in a certain way in order to be able to do that. So when you take computer science courses in high school, which I hope that you will do, you will find that you're not doing all of the work just in writing code. You've got to learn how to approach a problem as well. At the end of this lesson, one of the students said, wait, I thought this was computer science. And I loved that she was being really honest, that her impression of computer science is that what we should have been doing was having laptops in front of us, pecking away individually at some kind of program. What's most important for students, especially in middle school, to understand is, yes, computer science does involve writing code to solve problems, but we can't do any of that if we don't know how to think about the problem. And that's something that I do feel like no matter what discipline you teach, you can teach those skills to help the students when they're taking a computer science class and learning how to code with Python or whatever the case may be.